Okay, we are a couple of minutes late, but we had a really nice discussion session after the last presentation, and that's also one of the merits of this conference, that we can do this again. So, well, Rod also agreed that we can run a little bit out, but not too much. So I will try to keep an eye on the time. My name is Thomas Reukman. I'm from Utrecht University here in the Netherlands, and I'm chairing this session. And the session has the title now, Research and Emerging Technologies. I noted when I went to the list of the speakers that there is, well, we start now with the only affiliation that has university in the affiliation name. So we see how really, looking back at the different conferences here in Rotterdam or at PEFTEC, we see how much this is really more absorbing into the industrial domain. But we start with a presentation from university affiliation here, and it's not then similar as announced in the program, but it's Tim Vaughn who's going to replace him. We stopped with Colorado State University and we start again with Colorado State University. So the floor is yours, Tim.
How about now? Perfect. She said I didn't have to hit any buttons. That was false. All right, so I'm Tim Vaughn. I'm with the Energy Institute at Colorado State University, and today I'd like to talk about the architecture and testing of next-generation high-flow samplers. So this project was motivated by the discontinuation of the Bacharach high-flow sampler. Bacharach's been in use since the 90s. It's still in use today, but support was ended with no plans for a replacement. It's the most commonly used commercial offering for direct measurement of emission rates. And the aging fleet and the current renewed interest in direct quantification of emission sources presented us an opportunity to develop an improved device. So CSU developed an open source prototype under CARB funding. And the idea was that a manufacturer would pick it up and sort of take it across the finish line. That didn't actually happen. Instead, we discovered that there were 3 completely new commercial offerings that appeared. And so along with our own prototype, we did some testing of those devices as well. So the principle of the high flow sampler is pretty simple. You want to quantify an emission rate. So you find an emission source, you completely entrain it in a flow, bring it into the device, and you want to simultaneously measure the flow rate of the total flow stream and the concentration of the emission source entrained, and then you get an emission flow rate for the emission rate. So in addition to measuring your flow and your gas concentration, you might want to record some auxiliary data, so GPS for geolocation. You might want to measure your temperatures and pressures to correct back to standard conditions. You might want to also measure the relative humidity if your sensor has any humidity dependence. And so this method kind of assumes that the air and the methane behave as an ideal gas, that the air and the methane are perfectly mixed when they hit your sensor, that the concentration measurement is going to be perfectly linear or accurately corrected over the range of use that you intend, and that the flow stream measurement is going to be perfectly accurate over its range, and that it's unaffected by the relative proportion of methane or gas and air that you're measuring. And also, kind of the important thing here is that the whole method's based on completely entraining the source, so you need to make sure that your source is completely entrained so that you're getting an actual measurement of an emission rate and not just a sample of gas. So we did some market surveys, talked to a bunch of different stakeholders and people who are interested in getting these, and we kind of found that what most people wanted was pretty similar but new version of the Bacharach high flow sampler. So extend the flow rate a little bit up on the high side, get a little bit better accuracy on the low end, but generally you're kind of just updating what was already there. Most people were pretty happy with it, just wanted to improve the performance. So we started off with the GVP 100 blower that was in the Bacharach as a starting point, mapped out our flow curve, and then looked for commercial offerings that would be able to come back in and extend that flow range. We found this Delta fan and the SAN-ACE fan. Once we did a little bit of testing with all of our hoses and attachments on, we found that the SAN-ACE fan was going to be the better choice. So we went with that one and designed around it. We decided to use an orifice plate flow measurement device. Basically, it's pretty simple. It's well characterized. You can look at an AGA standard or an ISO document, and it sort of just guides you through it. You use the right geometries, you're going to have a a good starting accuracy, and then you can come in and do your own calibrations and improve it even further. So with our cataloged empirical discharge coefficient, we did some ASTM dilution calibration, and we saw that we were a little bit off, but pretty close. And so we came back in and did our flow rate as a function of, pressure differential, and we were able to correct that back to having a really good response. So with flow in place, we now need to measure our concentration. And for this, we obviously are trying to prove the low-end accuracy. So we avoided the low-end kind of generic metal oxide type sensors. At the same time, we want to be cost-effective and not be huge. So we're not going to put in a full-fledged tilde system or cavity ring-down spectrometer. That kind of led us in the middle to your typical kind of integrated sensors at the can and OEM modules and the like. And then again, we settled on the SGX INR ME100, which is just an NDIR integrated sensor. And then we had an auxiliary sensor, which was the Nevada Nano MPS, or Molecular Property Spectrometer. And the intention here was to use the MPS to sort of correct the NDIR for different gas compositions. It has a limited ability to differentiate between gas blends. You can't pick out an actual gas species, but it can deduce molecular weights, and that gives you an idea of what the response of the other sensor might be. It didn't quite work out in practice, but I'll get to that later. So with all that in place, we need a controller. So we need something for the user to interact with. We need to capture the data. We need to do some computations. We need to store the data. We might want to communicate it out to a database or to other instrumentation. So the software we wrote in Python. It runs on a Raspberry Pi 4 single board computer. Software is implemented using an object-oriented approach that you see on the right. It pretty much resembles the hardware architecture. Various custom classes interact with the individual sensors, allow you to calibrate them. You can go through the Linux APIs to get GPS data, control the pulse width modulation of the blower. For the GUI, you can enable and disable measurements. You can change the flow rate however you want. Calibrate either the sensors, look at individual sensor configurations and parameters on the different tabs. You get a real-time display of your leak rate and all your measurement parameters there. You can go ahead and do an auto measurement, which can be kind of whatever you want. You can have it step down in flows. You can have it try and optimize the flow rate to hit the target concentration that your sensor is best at, based on the flow geometries and stuff that you're looking at. And you can have cool yellow dots when it's actually measuring and purple when it's just in standby. And after you save the measurement, it's all going to go to flat CSV files with all of the raw data, along with summary statistics for the measurement period, and you can make those be kind of whatever you would like. Mostly just average and standard deviation for now. And so here's what it kind of looks like. Again, the idea for this is to make an open source prototype. So we're not trying to make the most sleek product. We want to make something that other people can make. And so that's why it looks as it does. So we've got a Pelican case here. We've got our flow inlet and then our orifice plate flow meter. We've got our pressure sensor port taps and our walls there, our battery, our sensor chamber with our sensors in it, and our flow exit. And if you flip the lid open on the top, you can look at the display screen. And this is kind of the hardware schematic over there. Basically, the brains is the Raspberry Pi and all of our other pieces. And like I said, it closely mimics our software design. And so here is it in its finished form. You can see the software running on the screen there with a touchscreen bezel. This one is not mobile optimized. It's a desktop app for now, but you can log into it on your phone remotely, and it works pretty well. In the future, you might want to put it on like a web app or something like that and make it a little more mobile friendly. We've got our custom sensor cards, and all of our other equipment is shown below, like I showed in the previous one. And the photo on the right is actually during the testing for the flow calibration. So that's our working prototype. With that working, we kind of want to test it, do some characterization. So we looked at 4 test areas, the limit of detection to determine the lowest viable limit for application. We wanted to look at the accuracy over the range of the device to understand, does it perform better on the low end or the high end or in the middle? What's a good application for it? And then we also wanted to understand the effect of different gas compositions on the sensors. And then finally, to test on some real equipment to understand, how it works when there's user interaction involved and when you get into a little bit more complicated scenarios. So for the first one, we just did limit of detection or lower detection limit. And we're going to kind of break this down into two sensors. Originally, we intended to use the nano to correct back the INIR. Didn't quite work out, but so we just treat them as two independent sensors in the same device. So really, it's like we're testing two high flows. And so we see a lower detection limit of 0.18 liters a minute for the INIR and 0.37 for the nano, which is kind of in tune with the relative performance of their specs. And note that this here, we're just kind of looking at a 50% probability of detection, not a lower limit of accurate and useful quantification. We also did that, but we have that on a different slide. You just kind of take a linear regression of the lower points and then use like 3 times the standard error of regression for that. That's in the final report if you're interested in that. And a bunch of data plots. So this is the accuracy quantification. We've got the CSU INIR on the left and the nano on the right. And the first thing that you'll notice is that in the upper right-hand corner of the upper left plot, we've got some kind of flyers there. That's basically just giving you back the total flow rate because the sensor has been pegged. It's not that it became optically dense, it's just that at the calibration with methane, you've sort of maxed out your reference 100% concentration, and then you've gone into the field and you've tested it with gas that has ethane and propane in it, and so now you've maxed out that NDIR sensor. And this is what we wanted to use the nano to correct for and avoid, but you'll see in just a second that didn't quite work. The nano didn't exhibit that behavior. It kind of behaved pretty well throughout the range, and so that gave us the idea to come back and do this testing, or to do this presentation as two different sensors. Both are good in the middle range, and showed them this. And the nano is a little bit low in the high range, but generally pretty linear. Probably can be corrected with some calibration. So here's the interesting thing with the gas composition response. On the left, you can see the CSU, the INIR sensor, is very sensitive to higher hydrocarbons. We've got basically 100% methane on that end and moving down to about 30% on this end, and our response swings by like a factor of 10. And the idea was to run the nano with the same blends and then see if we could, how granular we could get that. It turns out that we only got 2 different steps in the differentiation, so it was able to, we swung from 90% to 30% methane. It only gave us 2 steps, so it said this is a methane blend and this is a light gas blend. So that was probably not going to be useful to do our total, calibration curve correction and manipulation. So in the practical use testing, we saw a lot of variability, and also the INIR data is a little bit high, again, for that same reason. We're trying to characterize the performance of the device. We could easily calibrate that down, and the scatter would still be the same, but the slope would be better. For the nano, we saw, again, with the real equipment testing, a lot of variability in the data. And so that indicates that there's some other factor involved here, right? The performance was good on the bench, but when you put this in the hands of a person and go out and try and get them to capture real equipment, it kind of all goes out the window, right? So take it with a grain of salt, right? So I think I've covered most of this, but our important things to look at here are that the response to non-methane species is a concern. You need to understand what affects the sensor, and that your readings are being corrected and you're measuring what you want to be measuring, and to make sure that meets your needs and intentions, and that the sensor behavior and the device behavior in situ is going to be very different than it was in the lab when you have a human involved. And your flow measurement needs to cover a wide range of ambient temperatures and pressures and account for gas composition. And you want to match the device and operator's behavior together. Make sure that the operator understands and is using the device in the way that you intended, or you're never going to meet your overall device performance targets that you may have achieved in the lab. And so I'm getting short on time, but I'll try and go through quickly the field testing of the other prototypes. So what we did was we tested the Bacharach against the new Sensors Inc. Semtech High Flow 2, the Heatech Solutions Flow Sampler, which is a modern update of the Bacharach, and then the AdGlobe gas flow meter. We tested the 1.0 at first, and also the 2.0 later. So for the Bacharach, generally pretty good as the incumbent here. Good linearity over the whole range. Kind of poor performance at the low end, and then with the real equipment, a lot of variability and a generally low bias. And that was kind of common with some of the other ones too. Here we have the Sensors Inc. Semtech High Flow 2. We have really good linearity throughout the whole range, really good repeatability at different test points, and this one had the best low-end sensitivity of any of the devices that we tested. But again, on real equipment, we saw a little bit of a low bias, and that could be due to some human factors. For the gas flow meter 1.0, again, good linearity throughout the range. Maybe a little bit of an issue with saturation in the 1.0 like we saw in the CSU NDIR. Generally pretty tight, pretty good repeatability, and a little bit closer to 1-to-1, although with some variability on our real equipment tests. And most of this has been improved pretty well in the version 2.0 of this, especially with the density correction on. You get spot on the range that it's good for. Still a little troubling on the low end though. And then finally the Heat-Tech flow sampler. Again, modern update of the Bacharach, uses the same polyester-based sensor. Good linearity throughout the range, quite a bit of variability, some variability on the different test points and repeated measures, and kind of relatively poor low-end performance down there. And so I think that is my time, and thank you.
Thanks a lot, Tim, for the presentation of not only the CSU, but also the other high flow samplers. We move to the next presentation by Dr. Millington-Smith from QLM Tech in the UK. So the floor is yours. You will talk about laser applications, right?
Okay, good morning, everybody. Thank you very much for joining me. My name is Doug Millington-Smith. I am the Applications Manager at QLM Technology, and I have the world's supply of slides to get through, so I'll crack on. A copy of these is available by PDF if you would like it after the show. Where is my clicker? Here we go. So, we're here to talk about methane. Methane, as I'm sure you're aware, is horrible. Okay? It's a much more potent greenhouse gas than CO2, and the energy industry has dumped clouds and clouds of it into the atmosphere. We already know this, but it's not all bad, because methane gives us a silver lining. It's got a short lifespan in the atmosphere, meaning that if we can reduce methane emissions now, we have a measurable impact on climate change, and we can buy ourselves time to deal with the bigger problem of CO2. And this is what energy companies the world over are now starting to pledge, reducing their methane intensity by a certain deadline. But they have a really, really hard job, because methane is emanated from facilities in all different kinds of ways. Consider vents and exhausts, big, known locations, big amounts, possibly some temporal variation. Consider flares. Sometimes routine, sometimes non-routine, highly temporally resolved, often at height. Consider fugitive emissions. They can be anywhere. They can be big, they can be small, they can be widely distributed, they can be very, very, very localized. They can be happening for a very short period of time, they can be persisting for days. How do you find a technique which looks at all of these and measures all of these in a universal way? Well, the answer to doing this is to measure all the time. Look at it all the time. When leak detection and repair operations take place, they're typically temporally resolved. They tell you what's happening in the facility that day. What about tomorrow? What about the day after that? You need something which measures all of the time. But if that were easy, we'd all be doing it already. And there are a number of techniques which are approaching it from different points of view, all of which bring something to the party. Consider networks of point sensors. They're cheap. Consider optical gas imaging. That's really good at visualization in the right circumstances. Consider open path spectroscopy. Really good at concentration profiling in the right circumstances. Consider satellites. They can do everything. They can give you quantification and visualization, provided your emission is huge and you don't want to localize to any more than the size of this workspace. But there is no technique which is currently doing all of this at once. And this is what we feel the industry needs, something which can affordably visualize, quantify, and report on an automatic basis. And this is why QLM exists. QLM was founded in 2017 by our CTO, Zhao Ai. Zhao is now partnered by our CEO, Murray Reed, who has spent 30 years commercializing photonics in Silicon Valley. by Aaron Van Pelt, who helped build Picaro into the world-leading company it is at the moment, and Bernie Bolkin, who spent many years as BP's chief scientist and knows a great deal about emitting methane. So they're our strong leadership taking us forward. But what do we actually do? Well, we take two techniques which are well known and we combine them together in ways which are unique. And the first of these is Lidar, light detection and ranging. This work has been developed extensively for the autonomous vehicle industry and has reduced in size and cost drastically over the last decade. But Lidar normally only does range. It is many, many range-finding operations over a spatial area giving you a point cloud of what's there. But only a tiny amount of light makes it back to the detector, meaning that range is normally all you can do. Now, if you were able to get a detector which was able to process that tiny amount of light and do something more useful with it, maybe you can do something more with your sensor. Enter the SPAD. QLM's quantum advantage. SPAD stands for Single Photon Avalanche Detector. Think of it like a Geiger counter for light. So we take in those tens of photons per second, and using the SPAD, we are able to actually process them spectroscopically. Pardon my language. Now, if you take that spectroscopic information and you send out a LiDAR at the methane absorption wavelength, all of a sudden you have a spatial spectrometer which can tell you the concentration of methane in your point cloud. Lo and behold, this is what QLM do. So we take a low-power, very eye-safe laser, and we stash it in with some off-the-shelf components, and we build ourselves a tunable diode LiDAR, which will sense methane over a spatial area. Is that me? It is a very low-power laser. It's highly sensitive. It operates over a long range because it's a laser, and because it's mature technology in most cases, we are able to drive down our price as we scale up production. Come on. Come on. You know you want to. There we go. So our version 1 was released last year. It is a methane camera. It's about 40 centimeters long, weighs about 5.5 kilos. It sits on a hard point, a tripod or a pole or a fixed emplacement on a pan and tilt so it can move around, roving around. It is able to measure methane concentrations in a path-integrated concentration of between 100 part per million meter all the way up to 150,000 part per million meter, otherwise known as a gusher. It can do this up to about 200 meters range on land. We can also use the surface of the sea as well, up to about 150 meters. And it can take those concentration profiles, combine them with prevailing wind speed and direction data, and turn them into leak rate measurements of between 5 and 5,000 liters per minute with a relatively high accuracy. That's what we did. Now our journey is from can we do something to can we do it in a way that the industry actually wants. And this is how we put it to the test. Taking our GUI that was first built for laboratory operation, we can show you what the camera is seeing visually and with a heat map overlay of methane concentration as a function of the space it's looking at. Does it actually work? We need some help for this. So we enlisted a multi-user consortium called SPLICE, stands for Single Photon Lidar Imaging of Carbon Emissions, and it involves academic, technological, industrial, and government backing, all to take QLM's technology from the laboratory all the way into the industrial field. We make use of a couple of major sponsors during this. The two I'll be talking about today are NPL and National Grid. NPL are the UK's National Measurement Institute. They were established in 1900. And as a SPLICE project partner, they are providing technological consultation. They are validating our SPADs. They're characterizing our lasers. And thanks to the amazing Emissions and Atmospheric Metrology Group, thank you, John, we are able to test our equipment using their controlled release facilities, and they can provide comparative measurements when we go out to real-world facilities. National Grid are responsible for the UK's gas network. They have a great deal of pipelines, a great deal of above-ground facilities, and as a SPLICE project partner, they gave us, crucially, real-world testing facilities. And we are hugely grateful to Matt and his colleagues for providing us somewhere we can go out and test this in a real-world situation. But we didn't go there first, because there's many steps to make before we do that. The first step is, take a prototype out, do some controlled release testing where you know where the emissions are, where you know how big they are, and the challenge is simply, does the camera give you the right answer? We did this back in 2020, and we were able to visualize and quantify emissions at different ranges, different rates, different wind speeds, with a relatively high accuracy. The graph here of measurement accuracy as a function of actual release rate shows a pretty good correlation. The only time we don't is when we get down to really, really tiny emissions. But this is seal conditions. This is the easiest way you can do it. Let's make it a bit harder. We went out to Total Energies, to their TADI test facility, where they do controlled releases, but they do them blind. So they will tell you when they are releasing gas, but they will not tell you how much or where from. And the challenge is to detect, localize, quantify, and report that. In 2019, we went there, and we did some measurements in black and white with color over the top. In 2020, we went back there and did some measurements in color with color over the top. I can't tell you too much about the results we got because they are still under confidentiality with Total Energies. Merci bien. I look forward to working with you again in the future. The next stage, even harder, no controlled emission. A real-world facility where emissions are expected but not known. This is what we did with National Grid. So we went there to the Bacton test facility, ourselves and NPL, and we carried out a joint study. QLM used our camera, NPL did a comparative walkover study. And we looked to see what we could see, what they could see, and how they compared and contrasted. We saw a bunch of emissions. These were emissions at height and planned vents and exhausts of many thousands of litres a minute, but extremely short duration. NPL carried out the walkover study. They found a few emissions down at ground level that we did not see because they were too small. They were below 1 litre a minute. That is below the measurement limit of our camera. But they didn't see any of these, and they weren't expecting to because these were at height. So they couldn't reach them. They couldn't, and in the case of the vents, they couldn't go near them. So the QLM camera was able to see all of these emissions that your standard walkover study not only could not see, but was never really designed to see. We didn't limit ourselves to oil and gas. We went to Severn Trent's Minworth facility, the biggest water treatment works in the UK. And we put our camera in position for 1 day and had a look at what we can see. Lo and behold, we saw some leaks. We saw some leaks coming out of their tanks, their anaerobic digestion tanks. They were so pleased that we found this, they let us use this information. We also saw a kind of miasma of methane hanging above the tanks, and that provides us more developmental challenges. How do we quantify that non-localized methane, something we're still working on? The ultimate challenge is detect, localize, and quantify with your hands off, when you're not actually operating the camera. And this is what we did recently at METEC. Clay Bell and colleagues talking about the ADED program, where they did 3 months and a bit of blind releases, where the challenge was to detect, localize, quantify, and report the emissions without actually operating the camera. The camera had to do all this independently. What Clay didn't tell you is just how difficult this is. And what I'm really pleased to say is that we managed to succeed a number of times. So we were able to find a large number of leaks over the course of the 3 months. Some of them were so pretty we even made animated GIFs. You can find these on our LinkedIn site. But we also saw a number of different releases of different sizes, everything from less than 1 kilogram an hour up to a lot of kilograms per hour. And the results are still under analysis, so I haven't got values for you here. But this is the kind of imaging we've been able to see. And these images are also on our Plume of the Week on our LinkedIn site. So I'm going to skip past this because of time. Come on. There we go. So where do we plan to go in the future? Well, in the future, currently our equipment is about 4 kilograms and about 40 centimeters long. You can't mount that on a drone. We intend to make it smaller and lighter so we can do so. It's a way away, but we're working on it. We're intending to make it intrinsically safe, so you can deploy it in hazardous areas. At the moment, you deploy it in a safe area, you look into the hazardous zone. But once we have an ATEX or an OSHA version, we can deploy it on oil rigs, on offshore facilities. We're going to further develop the software so we can further integrate it into site safety systems. And so it doesn't just email home, it will send a text to the operators. It'll send an RSS to staff coming on duty. And we're also going to expand the range of gases that we can measure. At the moment, we can do methane, and we can also do CO2. There are so many other gases that it's going to be useful to measure in this way. Consider the ethane, carbon monoxide, hydrogen sulfide, ethene and ethine, reactive intermediates of the petrochemicals industry. In the environmental sphere, nitrogenous compounds, NOx, nitrous oxide, ammonia. All of these are within the march of SPAD technology. The lasers already exist, particularly in the mid-IR range, but SPADs are still catching up, and our academic partners in SPLICE are pushing us towards that. We anticipate being able to measure all of these gases over the course of the next few years. We are happy to have investment from a number of different spheres, both green technology and oilfield services, indicating that all sides are approaching this problem and see the importance of doing so. And it brings us to where we are now. So, through SPLICE, QLM enables organizations to achieve net zero through mitigation of greenhouse gas emissions. We have developed cameras which simultaneously visualize, quantify, and automatically report emissions of greenhouse gases back to a site safety system. We've trialed this at real-world sites, along with partners, the National Physical Laboratory and the National Grid and other project partners. And this gives us an increasing database of usable information to inform our industrial validation techniques. Look how far we have come. You're very welcome to join us and find out where we go tomorrow. Thank you very much for your time.
Yeah, microphone is on again. Thanks very much for the inspiring presentation. We will have questions later with all the speakers here. We will go to the next speaker, which is not Daniel Rüffer as indicated, but Marnix Valkeniers. But he's also from Sensiron in Switzerland, and he will talk about stationary sensors.
Yes, thank you for the introduction. So indeed, today I'm also going to talk to you a little bit about how you can monitor your methane emissions on your site with a fixed continuous measurement system, a little bit different from the last presentation in the sense that I will be talking about point sensors. But so first I'd like to introduce a little bit our company. So Sensiron Connected Solutions is a daughter company of Sensiron, which is one of the world's leading sensor manufacturers, active in a range of industrial applications like the automotive sector, the medical sector, HVAC, but also another wide range of industrial applications, like, for example, also our colleagues of Q-Micro are here with gas composition analyzers. So, and they have then founded a few months ago Sensiron Connected Solutions as a daughter company, which is focused on developing Internet of Things end-to-end sensing solutions, like our Nubo Sphere solution for methane measurement. So to go a bit more in detail on Nubo Sphere and what the solution actually entails, as I've said, it's actually a network of point sensors that consists, as a solution, consists of three parts. So first we have obviously the hardware, the sensor nodes themselves, the point sensors. Then we have the advanced analytics, the algorithm side. And then we have, after the advanced analytics, we have the full emission management, the user dashboard. And these three factors together, they work together to provide the network, the sensor network solution, which is very high performing, easy to use, as a very low total cost of ownership. And as you will see in our hardware especially, we have gone for a very future-proof design. Now, first let me explain a little bit, it's been explained a little bit already in some past presentations today, but just how does this solution work with a network of point sensors. So basically what we do is we install a number of sensors around the site that needs to be monitored, and then the wind will actually carry the methane plume that is coming from emissions towards our sensors. And then the advanced analytics will take the concentration measurements of the different sensors that are installed on the site, and the algorithm from there computes with the wind data that we have from the wind sensor that's installed on our sensors, computes back to the emission source, the location, the emission rate. So the detects the emission, determines the location and the emission rate of the emission through the algorithm. So that's how the system works. Let's take a bit of a deeper look into the sensor nodes themselves, into the hardware. So as I mentioned, we have a ultrasonic wind sensor on our sensor nodes. Generally, we have 1 or 2 wind sensors per site installed on the sensor nodes themselves. Each sensor node has its own solar panel, so it's designed for autonomous operation, also under very harsh environmental conditions. And then we have the sensor module itself, which has LTE connectivity, and which we think is very, very interesting for future proofness, is the sensor cartridge design. So each node currently still works with a MOX sensor in the sensing cartridge, but obviously we wouldn't be a daughter company of one of the biggest sensor manufacturers in the world if we weren't developing our own sensor for the future, which will be based on an optical principle, and which we think will have, especially from a data analytics point of view, a lot of advantages towards or compared to the MOX sensor that we are working with now. And then due to the cartridge design, it would be very easy in the future when the new sensor is there, when the optical sensor is there, to just replace the cartridge, and then we have the new sensing technology in any equipment that's already been installed up to now. And then, as you can also see, we have actually 2 slots. So in the future, we'll also be looking into developing sensors for other gases. Could be, as also mentioned before already, could be H2S or ammonia or benzene, anything that could be interesting to clients. And then we could have multiple sensing cartridges in each sensing node. So, as I also mentioned, we're looking very much into user friendliness. So the entire system can be set up very fast and very easy in less than 10 minutes. We have a very nice YouTube video of it as well, where you can see one of our interns installing it without prior knowledge and nothing more than a screwdriver in a few minutes. We work with plug-and-play LTE connectivity. Every sensor has its own GPS. And what you might be wanting to know as well is how many sensors do you actually need to monitor a site? Well, obviously this depends on the size and the complexity of the site. But to give you a bit of an idea, on, let's say, a standard upstream onshore, obviously well pad site, we would install 4, 5, maybe 6 sensors for a very large site. We, for example, also participated in the GERC test project in Zelzate, and there we had, for the compressor station, 9 sensors installed. So just to give you a bit of an idea on how many sensors are needed. Then, the second part of the solution is, of course, the advanced analytics, the algorithm. So, as I was explaining, we would have multiple sensors on site, at least 1 wind meter on site, to give us the wind data, the strength and the direction of the wind as it's happening, and then gather the concentration measurements from different sensors. Now, as we're still using a MOX sensor, it has some limitations, including sensor drift, and that's where we think we're also, at the moment, really differentiating from our competitors who are also using MOX sensors, as, again, we're a daughter company of one of the biggest sensor manufacturers in the world. We know about MOX sensors. We know a lot about how they work, so we're very particularly good at refining this MOX signal, and which means that we don't need to calibrate these sensors in the beginning or when they're already on site. So we can have our sensors, keep them on site without needing to go back for calibration, which is especially useful in very remote sites. So after the installation, basically you can leave the sensors there and you don't need to go back for recalibration or maintenance. So okay, so after the signal refinement, then is when the actual plume modeling happens through our algorithm. And from that, our algorithm automatically localizes and quantifies the emissions. Now, because it's still an algorithm, and we're obviously constantly developing it further for different applications, we tend to always have it supervised by our data scientists. So it's automatically detects, localizes, and quantifies the emissions, but we try to keep, we have always our data scientists to still supervise any results that come out of the algorithm. And then this brings it into the visualization and the alerting. So that's actually our user dashboard, the third important part of our Nubo Sphere solution, the emission management dashboard. So this also is something that we've learned from the operators we work with, and the test projects that we do in actual operators. That's a very big pain point, is visualizing the data and getting actionable insights from the systems. So that's why we've also put a lot of effort and a lot of focus into this dashboard, making sure that it's very easy to work with, gives actionable data, notifications to the operators when they need it and what they need. So in this sense, we have in this dashboard, we have the online dashboard and the app. The operators can track their sites. They can track the sensors that are on the sites with the wind sensors and with the wind meters and the sensors without wind meters. We have a feedback loop in sensor health. So if there is any problem with the sensor or with connectivity, you can follow it in the dashboard. And we give when we detect a leak, you can follow the status of the leak. First, if the algorithm detects a leak, then if it's been verified by a data scientist, you can see the emission rate or the estimated emission rate in kilograms per hour. And then you also, as an operator, if you've gone and you verified that the leak or that the emission was there, you can accept it into the dashboard, and you can also, in the dashboard, confirm that it's been repaired, so that actually the system can reset, and if it detects a new emission, we know that this actually is a new emission because the previous one has been solved. So that, in a nutshell, is the full solution. Now, well, what benefits are there to you? I think this is something that, after all the presentations I've already been here at the conference, should be quite clear. But more specifically on a continuous solution, the main benefit is that you detect your emissions much faster. So if you are doing intermittent or periodical surveys and you detect an emission, you don't know how long the emission's been or the leak's been emitting. So it could be that you detect an emission if you do every 3 months an OGI survey and you find a leak, you don't know if it's been leaking for a day or for 3 months, basically. So with a Nubo Sphere or with a continuous solution, you can detect the leaks much, much faster, repair them much faster, and thereby save on emissions and also on costs. So that's a bit the main selling point from an LDAR point of view, but then of course also from a measuring and reporting point of view. There's been a lot of talk as well on the OGMP 2.0 level 5 and reconciliation between source level measurements and site level measurements. Well, our solution could also be an ideal site level measurement technology for reconciliation purposes, especially in those sites where you have intermittent emission sources. Having a continuous measurement, continuous site level measurement over a longer period of time will give you a much more accurate picture on the total methane that was emitted over a period, which would really help in reconciliation and reconciling these site level measurements with the source level measurements. So I think those are the two biggest benefits of using our solution compared to other technologies that are available on the market. So I'm a little bit ahead of time even. But so that was my presentation. I hope I've given you a good short insight into our technology, what it can do, what it can mean for you, and we'll be happy to answer your questions after the next talk or anytime if you want.
Yes, thanks Marnix. Indeed, we will have the questions after the last talk now, which is by Sandvig Nielsen, who is one of the co-founders of Weel and Nielsen, Weel and Sandvig, sorry. No, I mixed it up, but it's also wrong in the program here. And he will talk about the issue that was already mentioned in Peter's presentation this morning, the measurements on turbines.
Thank you very much, Thomas. And yeah, I'm very happy to be here today, and also very pleased to have this opportunity to present the joint work that we have been carrying out with the BP on this important area of methane emission. So basically we have had, for the last couple of days, a lot of stories about the discrepancy between the top-down approach and the bottom-up approach, and in particular the bottom-up approach where you are based on emission factors. So I think that was a perfect backdrop for my presentation, as we are going to present a methodology that would significantly have the potential to close that gap between the top-down and the bottom-up approach. And the technology I'm going to talk about is what we call predictive emission monitoring systems, or in short PEMS. And I'll give a little bit discuss at a presentation about the technology itself, and then the work with BP, and lastly but not least, the results that are coming in from the first applications in Oman. Let me see if I can. Yeah, like many other companies, BP are publishing their emission data, and I'll not go into details here, but only saying that this is for the North Sea operation. And the only thing I want to note here is that we have two things. We can see that there are actually significant methane emissions coming from the facilities. But secondly, we also know that all of these data is mostly coming from emission factors. And as we discussed before, the uncertainty is huge on these emission factors. And as Peter's mentioned, that BP wants to do better. Wrong. There goes. So BP has formulated what they call the aim for statement, or the pledge. And basically what they want to do is to install methane measurements at all sites, and that is already by the end of next year. And BP is working both on the top-down and the bottom-up, as we have seen. And in our work, we are working on the bottom-up approach. And in particular, we are working on the turbine and the gas engines, and then there's a parallel project going on with the flares. So basically, we are looking at a system that will be deployed that will provide real-time methane monitoring measurements. So BP will be able to continuously, minute by minute, see what is the methane emission from each individual sources, and that will be across the entire upstream operation from BP. And one of the important things also that was mentioned earlier, that BP is also part of this aim for pledge, is that they want to be very open and transparent in what they are doing. So it's not just about reporting data, but also reporting the methodologies, and also introducing that, allowing other people to assess both methodologies and the data. So looking at the opportunities, I think at this point we all agree that emission factors are not sufficient, to say it at least, the least. So that leaves us, we need to have some system where we are actually able to capture the actual emissions based on the actual operating conditions for the turbines. And that leaves us with basically two options. And you see, traditionally, we have had compliance emission monitoring systems based on instrumental use. So we're extracting gas from the stack, send it down to the analyzers, and then do the readings. And this has been used for decades, and it's giving very high accuracy. It can give very high accuracy, but it's very maintenance intensive, and it's also quite costly, and even like for application offshore, it's almost impossible in some places to install. So that leads us to and also what the background for developing other alternative methods. And one of these methods is the PEMS, or Predictive Emission Monitoring System. And this has been used for, we have been working with PEMS technologies for 20 years now, and has been basically used for compliance monitoring, as I mentioned, for NOx, SOx, and so forth. It can give the same kind of accuracy as the traditional monitoring system, and it's also auditable, and there are international standards to demonstrate and validate the systems. So if we go a little bit, don't have that much time, I'll just go a little bit into the technology involved in the PEMS systems. So instead of using physical measurements from the stack, we are relying on existing sensors already placed in the gas turbines. A gas turbine has a huge number of sensors available, and we can use that combined with a mathematical model to actually calculate what is going on in the combustion process, and from that calculate the emissions. What we're doing, and all PEMS systems are used combining the models with temporary stack sampling, so to calibrate and also for validation purposes. And when it comes to different technologies, there are a number of different technologies within the PEMS system. So we basically have two types. We have the black box, where you're just looking at trying to sample getting a lot of stack sampling, and then record all the process values, and then build an implicit model relating the input with the output. The advantage is the model itself is you don't have to know much about the emission sources, and the model development is limited, but then to actually train the system will require a significant amount of stack testing. So on the other hand, we have the first principle method, where we are instead of relying on physical relations. So we're using energy and mass balances to calculate what is going on into the combustion zones, and from there we can apply reaction equations, and then we can precisely calculate the concentration in the stack. And again, we are still using stack testing to validate and calibrate the model. But with the first principle model, we are able to significantly limit the amount of stack testing that we are doing, and it's very important if you're looking at remote sites and offshore applications. So I say in our case, we tend to use the first principle model, and that's also what we have been developed together with BP for this project. So we have basically two kinds of emissions when you're looking at, and also what we say that simple emissions are those what we call the stoichiometric emissions, where we can simply calculate the emissions based on the flow rates of the fuel and composition of the composition of the fuel, and then on the airflow rate. So, for instance, we know also if you have sulfur content in your fuel, all this sulfur will basically end up as SO2 in the stack. So that's the simplest thing to implement in a PEMS model. The more complex is what we call the rate formation emissions, where the actual emission is depending on the condition in the combustion chamber, and also in how it's the design of the combustion plant chamber and so forth. And that is typically that's for the emissions like NOx, carbon monoxide, and of course also for the methane. And if you look, I don't want to go too much deep into the detail, but monitor or calculating and the methane is on the surface very simple. So methane is just coming from incomplete combustion. So if you can just calculate the combustion efficiency, then we have more or less directly the methane emission. But we are talking about combustion efficiency from 99.9 to 99.999 or something like that. And it's very important to this small amount. So in this case, it's getting more complicated. In our system, we are dividing the combustion chamber model into different zones, and then we are applying the equations in individual zones and combine them to calculate the output, the total output. And again, using stack measurements to actually calibrate the PEMS model. So we have been using this model that has been developed during this project. We have been using PEMS for, as I said, for decades, but the methane modeling is quite new. So it was very important that we could start up doing some real site tests. And with that, we have done that in Oman, where they have 9 gas turbines. We did the stack measurements using the best technology we could find to do the methane measurements, and that was the FTIR technology. Due to COVID, we were not able to travel ourselves to do it, so we actually had to train like local staff in Oman, and that was working very well, surprisingly well, I would say. But what we do the stack testing, we want to capture all kind of operations, so we are looking at different load levels and even also some startup and shutdown sequences. And then at the same time, recording the process values and use that for the model development and model calibration. And very interesting, and we are very pleased to find that we were actually able to calibrate and demonstrate very high accuracy for our PEMS system for the methane. So basically, we can see there's a very good correlation between the methane, the stack measurements, reference measurement, and the PEMS output. The big variation is some variation in the stack measurements. The system in Oman is also going to be used for compliance monitoring. So we have also calibrated the system. The same system that is used for methane monitoring can, of course, be used for the other monitoring other components. So what have we learned from the exercise here in Oman? First of all, as discussed earlier, there are significant variations in the methane emission from this kind of equipment. So we go from startup and low load, you can see emissions from 550 up to 1,000 ppm, and then we have in the normal operation or high, medium to high load, we have very low emissions, and actually we have a large period of time where we have emissions from the methane emissions from the gas turbines that are lower than the ambient methane content. So in fact, in these cases, the gas turbines are not like a methane emission source. It's actually a methane emission sink. And I don't know how to handle that, but that's something to think about how that would be handled. And of course, the good thing in our perspective as a technology provider is that we are able to build a PEMS model that was actually able to capture this variation. But we also know that we are just looking at at the moment, we're just looking at one kind of gas turbines, and we know there are more other out there, and we'll shortly be starting a new series of measurements in Azerbaijan, where we are looking at low NOx turbines, and later we'll be going on also to do gas engines as part of this project. So in summary, I can say that we have demonstrated that PEMS can be used as a viable solution for bottom-up measurements. And what we have provided, or we are providing, is a real-time online system, so BP will be able to see minute-by-minute emission from different emission sources. And last but not least, I see my time is up, but I would say a very important part also of this project is that we are having an external independent uncertainty assessment done, and that I think that will be finished within the next 1 or 2 months, and hopefully we will also be able to report on that, or BP will do it as a part of their aim to be open and transparent. Thank you very much, and I just want to also lastly say this is a significant team effort. So, and especially I would like to thank the team. Within BP, and especially the guys in Oman who took the job upon them to do the stack measurements. Thank you.
Yeah, thanks a lot. Can I ask the other speakers to come to the podium? Thanks everyone for keeping almost perfectly in time. We didn't run 1 minute more late than we were at the beginning of the session. So we are now, we have some time for questions. Who would like to see? Yeah, there's a question back there.
Just quickly, first, we actually have our first question coming online, which I believe is directed towards Doug. Chris says, at Total Energies, we see great potential in QLM technology. Is there a certain date the version B will be ATEX certified?
Yes, there is. I don't know what that date is yet, but there certainly will be a date. It's something we're working towards at the moment. The version B is being designed with ATEX in mind, whereas the version A wasn't necessarily. I'd anticipate it's going to be sometime either at the end of Q4 this year or Q1 or Q2 next year. That's my very conservative and extremely broad estimation. I can't be any more certain than that, I'm afraid.
Cool, thank you.
There was another question back there.
Yes, hello. Thanks for your presentations, guys. It's a question directed to Jan, if I can. Regarding the data-driven sort of methodology for PEMS development, I can understand how that works very well for NOx emissions because you can almost correlate that quite accurately based on your exhaust temperature, on your load, and see the emissions profile across the engine. How does the model do the same for methane? Because it's a lot more dependent on the efficiency of the machine. How does it take into account things like hours since water wash, the condition of the axial stage blades, and things like that, which vary quite a lot depending on running hours and other parameters?
Yeah, for me, first of all, I'll say that we are not using the black box methodologies. We are actually looking into what is going on internally in the process, and we are taking, I think, 10 to 15 different input parameters to be able to cope with the exact things that you are talking about. So we know the effect of having also, for instance, running anti-icing and like that. So we're taking into effect all these things into the model. So basically we just need to know what is going on and going back to calculating what is actually going on into the combustion process itself.
Okay,
I don't know.
That's fine.
Okay.
Thank you. No anti-icing and no man, I think.
Another question here in the front. Maybe while the microphone is changing, I can add maybe a question to that, Jan. What are, well, in direct measurements, you have interferences from other components. So you have shown us a very convincing case where it works. What are interferences and how often do they occur, and what are the not so successful sides of the methods?
But I'm not sure, because the interference, are you talking about the measurements themselves, stack measurements? Because there we know that it's a challenge to measure.
I mean in your
our model,
sensors, yeah.
So we have, so in the system, and I could spend a lot of time this explaining, but we are relying, the uncertainties in our system is coming, that we are using different sensors, and then we are using that to calculate. So what we are also having in the system is a reconciliation system where we are looking at all the input values and see if it will match up for energy and mass balances and stuff like that. But of course there are some uncertainties involved that, and that's part, I think, part of this ongoing work now to see from external side to see what we're doing. But the idea is to, of course, we have to do the real stack measurements, and also it's also validated against stack measurements.
Okay, thank you. There was another question here.
It's for Doug. What's the spatial and temporal resolution of the measurement, and how many measurements get averaged to get to your one quantification?
The answer to that depends on what's defined by a measurement. We're recording many thousands of points per second. The shortest time at the moment that we can do between measurements is around about 60 seconds. And the smallest spatial resolution that we have demonstrated in the field is about 2 square meters. The smallest spatial resolution we demonstrated in sealed conditions is about 2 square centimeters. So I know it has potential to be a lot more effective than it has been in the field so far. We are making a measurement of gas concentration, I believe at 2 hertz. and so it's around about 100 measurements as a bare minimum. I will point out, full disclosure, it's better if you look for longer. If you go to a 3 or 5 minute measurement, the accuracy goes up, the uncertainty goes down, but the bare minimum is about 60 seconds.
Question for Jan is about the repeatability of the measurement. So once you've gone through this process for a single type of GTG or GT, can you just apply that to that same make and model anywhere else in the world, or do you need to go through the same process every time?
It would be nice if you could just do the same, but you have to go through the same process every time. Because especially when we're talking about methane, because methane is just about the incomplete combustion. So even aging and stuff will have impact on the profile of the system. So you have to do the exercise every time and calibrate them, each gas turbine individually.
Another question come from online actually, from Daniel. For the PEMS system application for methane monitoring, does the system include consideration of methane in the intake air of the turbine?
Sorry?
For the PEMS system application for methane monitoring, does the system include consideration of methane in the intake air of the turbine?
Yes, certainly. And as I said, for the turbine in normal operation, it will be actually destroying the methane coming from the ambient. So it is taken into consideration specifically.
Thank you.
Yeah, there's one more question, then maybe we should round up.
So just a question for Doug. I quite liked your presentation. Looks quite a nifty bit of kit, to be honest. I was just wondering how your presentation showed, leakages from tanks and from fugitives and open-top vents, etc. How applicable is it to looking at uncombusted gas from flares?
I am limited by how much I can say of that for industrial confidentiality purposes. However, you can maybe join some dots. We have a methane camera, we have a CO2 camera. They can certainly look in the same direction at once. That is unfortunately all I can say on that topic.
Thanks a lot, everyone. Thanks again, the speakers. So an applause here. It's very nice, exciting to see so many solutions arising.